In the last lesson we looked at infinite limits, and we also looked at the difference between an infinite limit and a limit at infinity. And so in this lesson we're going to look at limits at infinity, and this is when your independent variable grows without bound and your dependent variable approaches some finite value. And so the informal definition of a limit at infinity basically says is if the values of f of x get as close to L as we like, as either x increases or decreases without bound, we say that the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. And so just like in the last lesson, we looked at some basic properties of limits, and the first one is the limit of a constant. And whether you're approaching infinity or a constant value, as in the last section, the limit of a constant is always a constant. And you can see here that as x goes to infinity, the y values remain the same, they're k. And as x goes to negative infinity, your y values remain the same. The next basic property we looked at when we were comparing infinite limits and limits at infinity, and this is looking at the graph of 1 over x, and as x goes to negative infinity, so as x gets extremely negative, you can see that your y values are approaching 0, or the x-axis, and as x approaches infinity, your y values are approaching 0. And so these are very good limits to know to evaluate other more complicated limits. All right. And in general, the last one we had 1 over x, but if you have some constant over x to the r, then the value of the limit as x goes to infinity or negative infinity is going to be 0. As x approaches negative infinity, you do need to be careful that your x to the r is defined, and we'll look at a scenario where that isn't in a minute. Alright, so the first one, example 1, the limit as x approaches infinity of 5 over x cubed is equal to 0. So let's first look at this function graphically. I've entered 5 over x cubed in my y equals, and I'm going to do a zoom 6. I'm going to just graph that in a standard window, and it appears that nothing is graphing, and I did this on purpose just to show you that sometimes you have to make sure that the equal sign is highlighted, and see right here the equal sign is not highlighted, meaning the graph is turned off. So I'm going to arrow over and hit enter, and then I'm going to arrow off just to make sure. Now that equal sign is highlighted, and I can just hit graph and graph this function. And so we can see from the graph that this function, as x increases, this function gets basically almost crashes into the x-axis. And so what I'm going to do, I'm going to trace on 0, and 0 is not a value in this function, but it's the center of the graph, so I want to zoom in just to get a little bit better idea of what's happening. All right. And if I wanted to I really care about not what's going on around 0, but what's going on at the edges of this graph, and sometimes looking at a table helps. So let's go in and look. We'll go to second table, and by the way, your table should, let's go to second table set for a second, second window. Make sure that you're on Ask and Auto, as we've been using all along in this course so far. We want to enter values and let the calculator calculate them for us. So I'm going to go back to the table, second table, and I'm going to type in 1. And I know that 5 over 1 is 5. If I'm going to approach infinity, I really want to jump a little bit more. So let's say we put 10 in. So if I have 1 over 10 cubed, that's 1 over 1,000. So that is shrinking quickly. If I do 1 over 100 and I hit enter, I'm already at 5 times 10 to the negative 6. That's a decimal point with 5 zeros. And so when I want to approach infinity, what I do is I just keep choosing larger and larger values for x, and at some point you can see here I'm getting 5 times 10 to the negative 9. That is a decimal point with 8 zeros and a 5, and you can see that this is approaching 0. So we can use our table to see that a function is approaching 0, or we could use the graph. We can do the same thing by, if we wanted to let this function approach negative infinity, I can use the same graph. I'm going to delete the values that I have in here. And I would start by choosing negative values. So I would start with -1, -10, -100. And you can see that our values are negative, but they are getting closer and closer to 0. -5 times 10 to the negative 6. And so as we approach from the left, as we approach negative infinity or positive infinity, this function is approaching 0. It also should make sense to you that if you have a constant in the numerator and the denominator is growing, that your fraction, the value of the fraction, is getting smaller and smaller, because you're taking a fixed number and you're dividing it up into infinitely many pieces, and so each of those pieces is going to be extremely small. The last one, as x approaches infinity of 5 over x to the 1/2, let's get this in our calculator. I'm going to go into my y equals. I'm going to clear this out. I'll do 5 divided by, now we can do 5 divided by the square root of x if we want. That's the same thing as having a fractional exponent of 1/2. I'm going to arrow out. So I've got 5 divided by the square root of x. I'm going to go second table. I'm going to delete the values that are there. And we'll do the same thing. We'll start off, say we put in a 1. 5 divided by 1 is 1. If I let x equal 10, I get 1.5811. X equals 100, I get 0.5. 1,000, I get 0.15. 10,000, and so to approach infinity, you just, what I basically do is keep adding a power of 10, and you can start to see if I approach 100,000, or if I let x equal 100,000, my function value is getting smaller and smaller. I'll type in 1,000,000, and then we'll look at a graph. So you can see here that these values are approaching 0. Let's look at this graphically. Let's do a zoom. We'll start with the zoom 6. Right? And if we want to approach, we want to see what's going on as this approaches infinity, we can change the window. This is a standard window, -10 to 10. Let's go into window. Let's start at 0, and let's let x max be, let's say 50. Start with 50. I'd like to change my scale. I usually let my scale, I take the difference between the max and the min and divide by 10 sometimes, or even 5, but I'll let the scale be 5. Let's graph this and see what happens. All right, we can see that our function is, as x is getting larger and larger, is approaching the x-axis, or the value is approaching 0. And you can change your window again if you'd like, and let it go to 100. In which case, I'd let my scale be 10. It just makes it look a little neater. Let's graph that, and you can see, again, we're approaching 0. There's a horizontal asymptote, and that's what's going on there. So the last problem I want to talk about in this video is the limit as x approaches negative infinity of 5 over x to the 1/2. So let's pull that calculator up again. Let's go back to a zoom 6 for a second. When we look at our graph, it doesn't appear that there are any function values to the left of 0. And this is basically because the domain of the square root of x is greater than or equal to 0. And since the square root of x is in the denominator, 0 is not in the domain of this function either. And so if I went into a table, and I'm going to delete these values that we've used before, and I start putting negative values in. If I put in a -1, I get an error. If I put in a -10, I get an error. And so for every negative number, I'm going to get an error because the domain of this function is all real numbers that are positive. So the reason why this limit does not make sense is because, again, the domain of this function is all real numbers greater than 0, or 0 to infinity. And so if you're asked to give a limit like this, what you should say is it really doesn't make sense. You can't approach negative values since they're not in the domain, your x values. Alright, in the next video we're going to start to look at horizontal asymptotes and compare them to vertical asymptotes.